Welcome to this presentation related to the application of RAINFLOW techniques to the design and operation of port infrastructure. My name is Carmen Castillo from the Universidad de Castilla-La Mancha, and my colleagues are from the Universidad Politécnica de Madrid and Oritian Boreas, all from Spain. The main ideas of this presentation are why focus on RAINFLOW, what is the definition of RAINFLOW, and how to apply it to port and coastal engineering. The concept of RAINFLOW, as we are going to use it here, it was defined by Reichlich in 1987, and it comes from the fatigue damage field, where it has demonstrated its power and nowadays is commonly accepted. Due to some similarities with waves, it has also been applied to port and coastal engineering, where it has shown some serious advantages over traditional methods, such as the zero-downcrossing method, but it is still not widely used. If we compare the zero-upcrossing method on the left and the RAINFLOW method on the right, we can observe larger ranges, that is waves, on the right. But we can also see what can be considered a series of waves with changing sea level. The same wave height interacting with a coastal structure at different sea levels have different effects on overtopping or damage progression of a rubble mound. Some of the applications of this method can be oriented to determining natural frequency oscillations in docks, wave groups, ship movements, overtopping increase, long period movements in armor breakwaters, and the damage associated with these phenomena. To define the RAINFLOW cycle, each local maximum in the sequence is paired up with one particular local minimum determined as follows. We select a local maximum, that is, point A. We obtain the previous and posterior points with the same level, that is, point B and point C. We calculate the minimum between A and B, which is point E, and between A and C, which is point D. And we finally choose the maximum of both minima, which in this case is point D. Once the concept of RAINFLOW is clear, we will be showing some applications. The first one being a comparison between the zero-downcrossing method and the RAINFLOW method. This figure shows red points corresponding to the zero-downcrossing cycles and blue ones for RAINFLOW cycles. Downcrossing cycles are all located in zone 4, since all minima are negative and all maxima are positive, whereas this is not the case for RAINFLOW cycles. Diagonal D1 represents the set of cycles with equal maximum and minimum. Therefore, there are no cycles in zone 1. The closer the cycles to diagonal D2, the more regular they are. Zone 2 corresponds to those cycles where both minimum and maximum are positive. Zone 3 corresponds to those cycles where both minimum and maximum are negative. Zone 4 corresponds to those cycles where minimum is negative and maximum is positive. Finally, we find Zone 5, which represents the highest waves which are not detected by the zero-downcrossing method. Let's see a second application which deals with operability related to ship movements. The picture shows a case of sway with several examples represented by numbers and located in the different RAINFLOW zones. The dotted line, which is the diagonal of the purple area, corresponds to the harmonic motion around the equilibrium point. The purple area represents motion crossing the equilibrium, while the yellow zones are the opposite, the ones that are not crossing the equilibrium. The arrows show the direction of increasing amplitude, red arrows, and increasing eccentricity, the purple arrows. This slide shows a comparison between the zero-downcrossing and RAINFLOW methods for all three rotating movements of the ship, which are pitch, roll, and yaw. Finally, some results are provided on the calculation of the operability in the case of sway using the RAINFLOW method, which, as you can see, is 31%. The third and final application is provided by using the RAINFLOW matrix to calculate damage progression. The RAINFLOW matrix, which characterizes each cycle in terms of its maximum and minimum, considers any possible oscillations no matter what the ranges or periods are. It is defined as the intensity of cycles with minimum I and maximum J. The calculations shown on this slide correspond to a second-order Markov chain. To obtain the RAINFLOW matrix, some steps need to be followed. The first one is the calculation of the upcrossing frequencies, considering three possible types of events. Then, these frequencies of the three types are combined to obtain the RAINFLOW count intensities, which are finally used to define the RAINFLOW matrix. The subscripts I and J refer to two sea levels, while K indicates a sea state. The different type of events refers to the number of jumps it takes to go from below level I to over level J, which can be 1, 2, or more than 2. Just remember that we are talking about a second-order Markov chain. Once the RAINFLOW matrix is known, it can be applied to the damage progression model, for example, of Melby and Kobayashi, as shown in the slide, with I and J being the levels and K being the sea state associated to the RAINFLOW matrix, which elements are underlined in green. So, to conclude, we can state that the RAINFLOW method can detect a wider range of heights and periods than other methods, which provides a better knowledge that can be applied to address both failure and stoppage modes, and therefore improve operation and reliability of coastal structures and port facilities. Some examples have been provided to show the applicability of the method. One related to a failure mode would be the damage progression on rubber mount breakwaters, and one related to a stoppage mode, which would be the one related to the ship movements and the calculation of port operability. Thank you for your attention, and I will be glad to answer any questions you may have.